of a light ray, we define ABC as a point on a wavefront. So you have a wavefront here, and you have a point ABC, and you have that phi equals a constant at time t initial. Now, as time increases, time increases, the wavefront that has a fixed value is gonna change position to another wavefront to maintain the value C. So suppose you take a point on the initial wavefront and you make it change position over time, so that at A0, B0, C0, you have that initial point on the surface. And then as t increases, suppose that this moves like a light ray, perpendicular to the wavefront. So let's call that RT. Let's take a normal to the wavefront as you take it as this is the gradient of phi for t initial equals 0. So let's suppose that t initial equals 0. And this here, and this quantity, so this is d phi over dx at ABC and d phi over dy at ABC. So this is normal, and we would like to normalize it so it becomes a unit normal. So we would say that RT is approximately equal to ABC plus unit normal times the velocity times t for small t. So the velocity, we know it's speed of light divided by refractive index. We can plug it in. And so suppose you have a general point and you fixed the value of the wavefront, but you vary time. Suppose that this is an arbitrary point on a moving wavefront where C is fixed but T varies. So you're looking at a point on the wavefront, and the wavefront is moving as time varies, and you fix the condition that the value of phi, the value fixed on that wavefront, is the same value as time varies. So to know how that arbitrary point has to vary in order to remain on that wavefront of fixed c as time varies, let's take the partial derivative of phi. So you want d phi over dt to be equal to 0. And so by the law of partial derivatives, you want d phi over dt to be equal to 0. This is a total differential. By the law by the chain rules, this is equal to the partial of phi over t, dt over dt, plus d phi over dA, dA over dt, plus d phi over dB, plus phi over dC. All these values are total differentials. And these are partial differentials. This is 1. So the equation simplifies to, we know that d phi over dt minus 2 pi f. We know that this can be written as a scalar product. This is d phi over dA. Rearranging, you find that this is a general rule, but suppose now that AT, BT, and CT, extra assumption. We suppose now that this is parallel to the normal of the surface. Another assumption, we assume now that ABC is the path of the light ray perpendicular to the wavefronts. So let's recapitulate. We do not know yet the differential equation for the wavefront, the phase. We want first of all, we want the wavefront to move as time varies so that its value stay fixed, so that the phase stay fixed. And secondly, we want that point on that moving wavefront to move in the direction of the normal to that wavefront. And the third assumption is we want that we want that the velocity to be equal to c over the refractive index. So if we were to plug that in that equation, we would want that the velocity should be in the direction of the normal, and it should be equal to that quantity. So if we plug in the equation, so what would happen is that plugging that inside would mean that you have this so the differential equation for phi actually depends on t. So the differential equation is where this is the refractive index. So you would want to have a full equation, and we know that d phi over dt is minus 2 pi f. So we know that the negative of that partial differential is 2 pi f. Grad, this here is called grad of phi. So we have grad phi, which this is actually equal to that, is equal to minus d phi over dt times the refractive index over c. So this condition that the velocity of a point of a moving wavefront, a point that moves normal to the wavefront, is actually given by that velocity. It's a constraint on the wavefront that tells you that wavefront propagates forward it propagates forward through its normals exactly at the velocity of the light rays. Of the light rays perpendicular to them. That's how the wavefront of light waves moves. You will measure that, you will see that wavefronts, suppose that wavefront has value 0 and this wavefront has value 2 pi. So remember that the light wave has the form, and so saying that this equals to 0 and this equals to pi means that, suppose that time is fixed. So you take light rays perpendicular to those wavefronts, and you will see that the amplitude will be a full cycle between the two wavefronts, because the phase, the value of the phase of the wavefront is exactly 2 pi. So you have a full cycle of the amplitude of the light rays passing through those wavefronts. And as t changes, those wavefront will move forward and will change forms. So as t changes, the wavefront will move forward, change forms, but there will be still a full cycle of field amplitude between them, since phi 1 minus phi 2 equals 2 pi.